Hello, this is Juhyeon Kim for Seoul National University. Today, I will present our paper titled Fast and Lightweight Path-Guiding Algorithm on GPU. Before talking about the main paper, let's firstly review the background. So, what is a rendering? In physical meaning, rendering is a process that calculates an outgoing radius LO at first hit point X toward camera direction omega O. According to the rendering equation, outgoing radiance is the sum of emitted radiance and integration of reflected incident radiance over the hemisphere, which is attenuated by BRDF, a function that defines how light is reflected at surface in cosine term with normal vector. Path tracing is a ray tracing algorithm that faithfully evaluates the aforementioned rendering equation using Monte Carlo integration. Monte Carlo integration numerically calculates integration by summing sampled function value divided by sampling PDF. Since it uses sampling PDF affects the variance of the final estimation. Ideally, we can achieve zero variance if we sample proportional to the integrand term. This technique is called importance sampling. For path tracing, considering the rendering equation, ideal PDF would be proportional to whole integrand term. However, since incoming radiance term remains unknown before rendering, so common practice is to sample only proportional to BRDF term. However, such method does not consider global geometry. It fails if there exists a blocker between object and light source, as the figure showed. We want to guide more passes to reach the light source, and we call this task path guiding. To achieve this, we have to learn and sample using incident radiance term. There are many previous works that had dealt with path guiding with sophisticated data structure, but all of them focused on CPU environment except a few cases. However, with the emergence of GPU ray tracing libraries such as NVIDIA Optics, more and more rendering applications will shift to GPU-based. In this paper, we propose fast and lightweight path guiding algorithm on GPU using simple GPU-friendly grid data structure. The figure drawn here summarizes our proposed method. Given a camera position and scene geometry on the left, we learn the distribution of radiance by ray tracing and store the radius distribution with the data structure shown on the right. We divide scene as a regular voxel, and for each voxel we store radiance distribution using uniform grid. We learn radiance using SARSA, one of well-known RL algorithm, which is fast and lightweight compared to other methods. Then, when we render the scene, we sample from the stored distribution using fast rejection sampling. The rejection sampling adapts the current surface normal to reflect finer geometry than the grid resolution. Let's first look at the radiance learning method. The process of path tracing is closely related to reinforcement learning, or RL. In path tracing, we iteratively shoot rays, find intersection, and then select the next ray direction until termination. In RL, agent at state S iteratively takes action A, turns it to next state S prime, and receives reward until it reaches terminal state. So can you find the analogy between two processes? Here is a table that clearly shows one-to-one correspondence. Ray direction and ray origin corresponds to action and state in RL. Emitted radiance can be thought as an immediate reward in RL. The incident radiance is evaluated as an expected accumulated emitted radiance during the path. Similarly, in RL, we define action value function, or Q function, as an expected cumulative reward. I will emphasize that incident radiance corresponds to Q function in RL. Therefore, we can make use of many RL algorithms that learn Q function to learn radiance and path tracing. Such task in RL is called prediction. It can be largely categorized into three groups. First, dynamic programming, where expected SARSA, which was adopted in Dam and Keller's work, aggregates all next incoming radiances using bootstrapping with n samples over a hemisphere. Since it involves the exhaustive aggregation over the possible next actions, It is computationally heavy. Second, Monte Carlo method updates radiance value to the final accumulated radiance after tracing full paths without using bootstrapping. Since bootstrapping is not used, it has to store all of the previous points, which may cause memory-related problems. For example, if maximum length of path is m, then it would require OM memory. Instead, we propose to use SARSA, one of the temporal difference methods that updates Q value to single bootstrapped future return. Unlike expected SARSA, SARSA only considers the single next state, which does not require aggregation. Since it uses bootstrapping, additional memory is also not required. Therefore, we can conclude that SARSA is superior to expected SARSA or Monte Carlo method in terms of speed and memory consumption. In fact, SARSA is not the most accurate approximation, but empirically the benefits of time and memory offset this problem. Now, let's look at how we can perform important sampling from learned radiance. Our goal is to sample rate direction using PDF proportional to product of following terms. We find the PDF by combining the learned radiance Li with surface normal, which is further explained in the paper. Then, to sample the PDF, we use rejection sampling, where we first sample from PDF that covers target PDF and reject invalid samples. Its time complexity is dependent to the acceptance rate. For simplicity, we use sampling PDF as a uniform PDF over a hemisphere. This figure shows rejection sampling with uniform PDF in 1D case. We sample point in rectangular area, reject sample that is out of the target PDF, which is colored yellow. To maximize the acceptance rate, we only sample point whose Y value is smaller than Pmax, the maximum value of target PDF. However, this method still rejects so many samples if sampling PDF and real PDF is largely different. Therefore, we propose a method to reduce rejection rate by mixing a uniform PDF. Here, one issue is determining epsilon, that how much we will mix a uniform PDF to original PDF. If epsilon is set to too small value, then mixing will be no use and too many samples will get still rejected. On the other hand, if epsilon is set to too large value, then learning radiance will be no use. Quantitatively, each effect can be represented as following, and the optimal epsilon can be found then maximizing product of two terms. Now let's look at experiment and result. We implemented our algorithms using our own renderer with NVIDIA Optics and Python using megakernel architecture. We tested 12 scenes in following site, and for evaluation, equal time budget is imposed over all experiments. For baseline method, we compare the BRDF method that does not use path guiding and quadtree-based method that stores radiance in quadtree in spherical domain. Since it samples without considering normal direction, it may contain invalid samples that heading down towards surface. Here is the qualitative result. Compared to BRDF or quadtree method, our method gives more reliable image. Quantitatively, interpreting average error value over whole scenes, we affirm that our method gives the best result. Our method is slightly slower than quadtree-based method, but it eventually gives better results thanks to zero invalid sample rate. Comparing our method without rejection sampling optimization or SARSA update, we could find the effectiveness of each proposed method. Here is more result for other scenes. Now, let's compare radiance learning method. Here, in addition to equal time budget comparison, we also compared quality of radiance map with equal samples. First, expected SARSA gives best radiance approximation, but it gives worst result in equal time condition due to its slow speed. Monte Carlo method gives better results than expected SARSA, but it turns out to have true problems, which is attributed to storing all of the previous ray information. Both Monte Carlo and Sarsa's time complexity is theoretically O1, while Monte Carlo seems empirically slower than Sarsa because of memory access overhead. Also, it becomes a serious problem if we use wavefront architecture that uses millions of concurrent reads. While Sarsa, our proposed method, gives best results in terms of error, memory, and speed. Changing epsilon in rejection sampling optimization gives an interesting result. If epsilon is too small, too many samples get rejected, and we can demonstrate it by checking number of samples decreases as epsilon goes to 0. If epsilon is too large, learning radiance becomes no use, and we can demonstrate it by light hit rate decreases as epsilon goes to 1. By considering both effects, we could find an optimal epsilon value near 0.5. Here is the conclusion. To sum up, we propose a simple GPU path-guiding algorithm that uses a grid structure. We propose fast and lightweight radiance learning using SARSA, and also suggest optimized rejection sampling that improves sampling speed. Thank you for the listening.